a more powerful algorithm for cube root, or really for any root, or really for any equation at all, was invented later on in China, and I'm going to show you how it could be used to find the cube root of 12,977,875, which is equivalent to solving this polynomial equation. The first thing to observe is that because, first of all, this answer is going to be between 100 and 1,000 because it has 9 digits in it, and to the nearest 100, or it's somehow, it's going to be between 200, because 200 cubed is 8 million, and 300 cubed is 27 million. So this is between 8 million and 27 million. So x is sort of 200 plus something, and we don't know what that something is, but if it's a 3-digit number, I'm going to say that y is going to be a multiple of 10, and z is going to be just a number between 0 and 9. So we're going to try to figure out the tens place and the units place. And the method is going to be pretty unusual looking, but I'm going to show you how this works. So we've established that x is sort of 200 and something. So what we do is we make a chart, and the chart looks like this. 1 because the coefficient of x cubed is 1, 0 because there's no x squared term, 0 because there's no x term, negative 1, 2, 9, 7, 7, 8, 7, 5. Then we write the 200 out here, leave a space, one line, bring down the 1. 200 times 1 is 200, 0 plus 200 is 200. So I'm multiplying, putting the answer here, and then adding these together. Again, 200 times 200 is 40,000. And then you add 0 plus 40,000 to get 40,000. And then 200 times 40,000 is 8 million. And you add these together, and you still have negative 4,977,875. Let me circle this number. Now we do it again, this time bringing down this one, doing 200 times this one, putting it here, adding them together to get 400. And 200 times the 400 is the 80,000. We add these two things together, and we get 120,000. And we circle that. Now we do it again, bring down this one. 200 times 1 is 200. Add them together, get 600. Circle that, and finally bring down the 1. What's happened? Well, these numbers become a new polynomial, which I'll write as y cubed plus 600y squared plus 120,000 minus 4,977,875 equals 0. And this polynomial is going to, the y value is going to be, we're going to find the multiple of 10 that gets this close to 0, and that's going to give us the tens value of this thing. I'll explain maybe in another video a little more theory of why this works. For now, this video is just about, here's sort of how you do it. So again, we know the answer is 200 and something. The answer to this new polynomial is going to be the tens place of our answer. And we do this new polynomial the same way we did the other one, so I write it down. It was y cubed plus 600y plus 1, 2, 0, 0, 0, 0 minus 4977875 equals 0. And as far as getting an approximation, this is a y here. As far as getting an approximation for what to try, unlike before where it was just cubed, it was just cube root, this one, what we notice is that this term is really large, the y term. So these y cubed isn't that big in comparison. So I'm just going to divide to get an approximation for y. The 4977875 divided by the 120,000. And when you do that, 4977875 divided by 120, you get about 41. Now, we want, so we try y equals 40. We want, ideally the answer becomes 0. When we plug y equals 40 into here, we get 0. We're finished with the question. The answer would be 240. If the answer doesn't become 0, if it's, we want it to be negative then, because that would mean that it's 40 something. So if you try 40 though, it actually becomes positive. So 40 into the equation makes this greater than 0. So we then want to try y equals 30 instead. And when you plug 30 in, you do get something negative, which means the answer is going to be like 30 something. So 40 was too big because it became positive, but 30 was too small in a sense, but it's the first one that becomes negative, so y equals 30 is our sort of next digit. Now what we do is we go through this process again. We write down the coefficients. 1, 600. I think I need more room for this. Coefficients, we're going to put the 30 here. 1, 600, 120,000, and minus 4977875. And we bring this 1 down. 30 times 1 is 30. 600 plus 30 is 630. 30 times 630 is 18900. Add these together, get 13,890. Multiply that by 30. Get this large number, 567,000. And when we combine that with negative 4977875, we get negative actually make this 13,890 times 30 is apparently 4167000. And when you combine that with 4977875, we get negative 810875. We circle that. Now again, we bring down this one. 30 times 1 is 30. 630 plus 30 is 660. 660 times 3 is 1,900. Sorry, 19,800. That's 660 times 30. 19,800. Add that to the 13,890 from before to get 158,700. Circle that. Again, 30 times 1 is 30. This becomes 690. Circle that. Bring down the 1. These four numbers become the coefficients of a new polynomial, still cubic, z cubed plus 690z squared plus 158,700z minus 810875 equals 0. This new polynomial has a solution that's a single digit. And if you want to approximate what z might be, you could divide 875 divided by 158,700, because this coefficient is so large, these other two guys are not, that big in comparison. 810,875 divided by that becomes about 5. And good news, when you plug 5 in to this polynomial, z equals 5 leads to 0, so it works. So z does equal 5, and that's the units digit of our answer. So the answer to the original question turns out to be 200 plus 30 plus 5, or 235. This process actually works for any polynomial equation, not just things like this. We could have started with an equation that looked like this, for instance, and it would work also. So it's a general method, and it doesn't just work for cubics. It works for anything, fourth, fifth. So it's a general method. In another video, I'll explain a little bit about why this works. This one's just how to do the algorithm.